whether this is correct or not, for the Stokes theorem. Stokes theorem is it states that the surface area integral or the flux integral of the curl of a vector field A is equal to the line integral of a vector field A across a closed path. So this closed path is going to enclose a surface area, and in this case, let's assume this configuration. So we have the XYZ coordinate system, the Cartesian coordinate system, and let's assume we have a closed path which goes from 0, 0 to 1, 0 to this point here and back to the origin. Now let's assume that the plane is on the the surface area where we're going to integrate is on the YZ plane, or whenever the x is equal to 0. Let's start. First of all, we can either calculate this side of the identity or this one. Let's take this first. Let's calculate the line integral of the vector field A across this enclosed path. So let's consider the first path, the first one. And first we need to identify what is A. A as a vector field is given by this expression, and now this is 1. Now we want to go along this path for A, and what we have there is that x is equal to z is equal to 0. So this is a given as we move this way. So if we substitute, if this is true, then A itself, it's equal to first x, this is 0, this will be 0, we'll have only 3y squared. So here we'll have 3y squared will be the A, and if we multiply this one, if we take the dot product of this one with dl, let's have a look. So this is 3y squared along the AY, and also dy or dl is also dy, okay? dy ay. So let me write this for a moment. This dl along the path 1 is equal to dy ay, okay? So if we take the dot product of this with 3y squared, that's all we get. So here we get another dy. So this is a dl. If we integrate this one, a dl, from 0 to 1, we get 3y squared dy. This is equal to 3 times, this is a dl. All we get y cubed. From 0 to 1, we get just 1, okay? So this is the first line integral. Then we go to the second line integral, and let's see if I can successfully erase this part. We make and we go to the second one, and here we have the second path. Over the second path we are talking about this one, and here we have x is 0 and y is 1. So if we check here, x 0, y equal to 1, the a dot dl, first of all, let's see, along this path, the dl, the line integral over which we will integrate, it's equal to dz az, dz times az, okay? This is the dl, and now which means that when we take the dot product of this dl with a, the only term that is going to survive is this one. So let's see what we have during this path. So a dot dl, x was 0, which means this term is gone, but this term will be gone because when we take the dot product of ay with this, it will be a null. So here we just get a dl. This will be here 4 times y is 1, is 4 times z squared. So this is 4 z squared dz. Then if we integrate this, when z goes from 0 to 1, this will be equal to 4 times z cubed over 3, that's the integral of z squared dz. From 0 to 1, we get 4 over 3. So this is the integral, line integral along the second path. Similarly, we go along the third path, which is going to be here. So we'll go from this point to here in this direction, and the line integral, it will still be, as we can see, the z stays the same, but the only variable that is going to change is dy. So we're going to have a situation which is similar to the first path, and along this path we have x0 and z is equal to 1. Different from the first step is that z now is not 0 here, but it's 1. And let's see what we get for a dot dl. A itself at these values, this is dl, a itself at x0, this term is gone, z is 1, so we get something like z is 1. So let's write this in detail. We get 3y squared, okay, this stays the same, 3y squared ay plus z is 1, we get 4y times 1 square, which is 1 times az. Okay, so this is a itself. We take the dot product with dl. dl, as we said, this is going to be dy, no, it's correct, dy ay, because the direction is pointing along this path. So then we know that az dot ay, since they are orthogonal coordinates, we can, the result, it will be 0. So let's take it out from here. And then here, what is left is that ay dot ay, it's 1. So we get here, we will integrate 3y squared dy. The integral is from 1 to 0. Then we get here 3 times y cubed over 3. These cancel out. From 1 to 0, we get 1. Sorry, that's 0 cubed is 0 minus 1, it's minus 1. So this is along the third path. Then along the fourth path, this is the ADL will be equal to, sorry, this is A dot DL. So let's have a look. And this along the fourth path, let me write it on this part. Let's see what we get. Along here, we have x is equal to y, and this is equal to 0. So let's see what happens here. If x is 0, this term is gone. Y is 0, this is also gone. Y is also 0, gone. So a along this path is completely 0. So any line integral of 0 with respect to dl, it will be 0. So let's not do this, but we can, respecting the space on the board, that's 0. So if we add up the line integrals over all of these four paths, we had a 1 here, we had a 4 over 3, and we have another minus 1 here. So if we add these up together, we get the answer. It's 4 over 3 will be this side of the line integral. Now, what we need to do next is that we need to calculate the curl of A. We need to calculate the curl of A to get this side of the equation. And let's see how lucky I am with erasing this one in less than 30 seconds, which I'm not always that good. Okay, so it is essential to figure out how we can write, even being able to write correctly the terms inside the integral for the Stoke's theorem and for the divergence theorem. That's essentially the tricky part, or the important part, which, if written correctly, will be good. Now, in order to get, if you get a pen and paper right now, as I'm trying to solve this one for all of us, what you need to do is to start to calculate the curl of A. And to calculate the curl of A in Cartesian coordinate system, it's a relatively simple task. So you just write it as if you're calculating the cross product between a del operator and the A itself. And since you're going to calculate the curl, you have a look at the A. So as I'm talking right now, you just look carefully at this A, and since you're calculating the curl, for sure, we know that whenever we take the cross product, for example, if you take the cross product of x and y, the result is going to be along the z, right? Because this is what the cross product does. So in this case, it looks like, since here we have the ay and az, it looks like we're going to have at least some component along the x-axis, okay? Just because, in a similar way, that a cross product along the x and y gives us a vector result along the z. We do remember these from simple vector properties that we covered in the first week of the classes. So now I think I was good into erasing the board. Sometimes it's the most challenging part of the lecture. Then we did it. Then let's see what we get. So the first thing was we need to calculate this curl of A. So here we get here the AX, AY, AZ. This is a derivative with respect to X. This is a derivative with respect to Y, with respect to Z. And then here along the A, apparently AX is 0. AY, it's 2XZ plus 3Y squared. And here we get 4Y Z squared. We calculate the curl, and for the curl, the result that we get, we have here along the AX, because this is how we are going to calculate it, and for AX we have the derivative of 4YZ squared with respect to Y, so we get here this is A squared times 4Z squared minus the derivative of this, let me have a look, derivative of this term with respect to Z. The derivative of this term with respect to Z, we have this Z here, which means that we just have here minus 2x. Minus 2x. Then along the Y, let's see if we are going to have any term along the Y. So we do this minus AY. And we'll take the derivative of this term with respect to Z, which is 0, because derivative of 0 with respect to Z, it will be 0. The derivative of 4YZ squared with respect to X is also 0, because we see no explicit dependence on X. So this is a whole 0, plus AZ. This is the third candidate for the direction of the curl of A. We could have gone a little faster in this part, but the AZ, we take the derivative of the, so here we'll just have the derivative of this term with respect to X, which is a pure 2Z. Good. So this is, apparently we can even take this away, but apparently we have the curl of A along the AX and AZ. Now the curl and this curl, we have to integrate this one over ds. Now what is ds? ds in this case, we know that the surface area is defined by a vector which is perpendicular to this surface. So you might agree that the ds in the vector notation, it's equal to whatever ds is times ax. So it will be a vector field pointing along the x-axis. We're using right-hand rule. If we're going in this path, the direction of the vector field of the surface area, not vector field, is going to be like this. So taking a dot product of this ds with the curl of A, it looks like pretty sure only the dot product of this term with this term will survive. This will cancel out. So immediately we can say that curl of A, this term, dot product with ds, this is going to be equal to 4z squared minus 2x times ds. Actually the ds, the surface area element, the smallest surface area element that we can consider, it could be something like this. Okay, this is infinitesimally small. What is this small area element here? It's dy times dz. Okay, so that's what ds is. So whenever we integrate, we're going to have here 4z squared minus 2x, and we integrate dy dz, and we have a double integral. They both go from 0 to 1, 0 to 1, and let's see what we get. So I think this part, it will be more straightforward than the rest. So we integrate the 4z squared dy dz minus the integral, let's take the 2 out, x. Actually, x over the whole integral is 0, so probably right away we can make this 0. We save also some effort and time and space on the board. And then here we know that this dy, it's equal, so cancel this out, we'll be left with the integral of dy, it's y. And then if we are integrating from 0 to 1, we get just a 1. So I can take this 1 out, which is the integral of dy, we have the 4z squared dz. This is equal to 4 times z cubed over 3, the integral of z squared dz. From 0 to 1, we get 4/3. So it looks like the left side of this identity, this is also 4/3. So it looks like the Stokes theorem stands for this vector field. So identity proved.